we have come to the conclusion of what we have been looking at, that we now have all the properties and the change in the properties. So we have defined many properties and we got change in properties for both vapor-like behavior and ideal gas. And that's what we were looking for. So what we can do now is use this data to go back to those equations that we wrote in the second module after the analysis of the laws. And now we are in a position to put numbers in there and start getting the answers. So this last part, as you see in the total problem solving process, is only one small little thing. The initial part where we formulated the problem, did the approximations and got the equations that we want to solve. If we made a mistake at that point anywhere, the next point where we put numbers into the equation doesn't really help us. So we have to be very clear on that part. After we are done with that, we say, well, okay, now let me put numbers wherever they come from, and we do this way. What I will do to complete the discussion on properties is to introduce two new properties. You might have come across these in physics or chemistry courses. One is called the Gibbs energy, and the other is the Helmholtz energy. Sometimes this is referred to as Gibbs free energy. Sometimes this is referred to by some as Helmholtz free energy, and in some text you will find this referred to as Helmholtz function. Gibbs energy is denoted by G. The specific Gibbs energy is small g. Helmholtz, we will use symbol A, but in some books you will find the symbol psi has also been used. We will use capital A for total Helmholtz energy, small a for specific Helmholtz energy. And these definitions complete the set of properties that we would like to have for a pure substance. The Helmholtz energy actually is much more attractive because it is from here that we develop that equation for a PVT curve, and then by using property differentials we calculate all the other properties of a pure substance. We do not need to go very deep into this, but one should be aware that this is the totality of properties that we are working with. So for completing the discussion's sake, I am showing these. So Gibbs energy is defined as H minus Ts, or G is equal to small h minus Ts, and Helmholtz energy is A is equal to U minus Ts, or small a is specific internal energy minus Ts. So what we have done something is in both cases we have somehow got something less than Ts. And this becomes important when we look at what is called the work potential of a reaction or work potential of a change of state. And this tells us what is the maximum possible work that we can get. In the case like a fuel cell or a battery, that's where this property comes in. This property also comes very important in looking at reactions, where we ask, if I burn the fuel in air, what is the species that I will get, what is the temperatures I will get, and the Gibbs energy will tell you what will be the final composition of that. This is also good for mixtures, and say, look, if I mix so much water with so much air, what is the pressure and temperature that I get? It's the Gibbs energy that helps us to get the answer. Okay, so these are the two functions, two energy functions that are there. And now I present a graph, a little chart, which summarizes all these properties that we have looked at. This is there in the notes. We don't need to really memorize or go deep into this, but it is good to know that all these things are there and they have an importance in thermodynamics. So here is a table. There is a property. Here is Maxwell's relations, interpretation of that property, and what functions came out of this property. So on this side we start with U. U is said is a function of entropy and this because du is TdS minus PdV, which means that U is a function of S and V. So that is U equal to USV. And by doing a little bit of small differentials, which I have given in the notes, which I'll put it up very soon, you get dt dv, and there's a bracket missing there, is equal to minus dp ds at constant volume. And you also get from there that temperature is du ds at constant volume and pressure is minus du dv at constant entropy. So that's what we begin to see, that how all these properties are related to each other by very nice mathematical functions. So if only we have a PVT diagram which satisfies all these things, just differentiation is good enough to get all the other answers. Okay, so this tells you that this is the internal energy of the molecule that includes its vibrational energy, translation energy, rotational energy, electrical energy, and any other types of internal energy that a molecule may have. That's all there inside this. To that we added PV, which we called as the flow work, as H equal to U plus PV, and we got this equation dH equal to TdS plus VdP, and that gave us the expression that dt dps is equal to dv dsp. Our temperature is dH ds at P and V is dH dP at constant entropy. And by looking at Gibbs energy, it's the maximum work that is possible from a process. G equal to H minus Ts, dG equal to minus ds dt plus VdP, and again we get these two differential equations. Our specific volume is dG by dP at T, and S is minus dG dt at T. And the last one is of the Helmholtz energy, A equal to U minus Ts, dA is minus ds dt minus PdV, and you get these two differential equations. And pressure is minus dA dV at constant temperature, S is minus dA dt at constant specific volume. I have listed here 4 more equations which are useful, and these are the equations that we start using to get from PVT diagram all the other properties that we are looking for. And the nice thing about using such a formulation is that if we have the right formulation, just a few sets of differentials and we get all the answers. There is no approximation involved, and this process is superior to saying that I take data and I do a polynomial fit. Polynomials are very badly ill-behaved between data points, and differentiating them could give serious mistakes. So we be very, very careful that if you are working with polynomials, whether it is for properties or any other case, differentiation is very, very dicey. Best to avoid that. Okay, how we got those equations? So this is one little thing. du is TdS minus PdV. U is a function of S and V, and we just differentiate it to get this part, and then we can put various other substitutions and you get this big equation. Don't worry what is there inside this, but we'll just see what it means. That if I want to evaluate U, I need CV0 as a function of T, and I can integrate it with temperature. I have this big expression which is what rho, P and T. Rho, P and T. So if I have an equation for the PVT relationship, I can put that and integrate with respect to rho, and this is some constant which is somewhat arbitrary. We can pick what we want. So that's how we do all these operations, and we get U. And similarly, there's a second function, how we get S from PVT data, just to know that such a method is there. S can be written from TdS equal to du plus PdV. We substituted that, then we did some more substitutions, and this we get that S is a function of CV0 as a function of T. That's what you need here. This is R ln rho. Rho is the density. We need density there. And this whole thing is an integration of density where you have rho and dP dt coming in over there. And then this one is a constant, depending on where the reference state is there. So what these two equations showed us is that if you have a functional relationship between P and T and rho, so P as a function of T and V, or P as a function of T rho, then we can differentiate it, put it in this equation, and evaluate entropy change. And this is valid for every state. There is no approximation here because we are looking at a PVT relationship, or this relationship that we have, which is good for all states. So we don't have to depend on somebody giving us the charts and the properties and the number. We have a little bit of entrepreneurship. We can make these charts ourselves. Okay, so that is two of the properties. And now I'll just give you some examples of how we get this P rho RT type of a thing. And what we have done is P equal to rho RT, which is the ideal gas equation of state. And we added to this big term here, and then which is Ci, which is some sort of a constant as a function of temperature, and another function which is of density. So we've done a separation of variables of sorts, and this is where, if you look up mathematics, you would have come across the Helmholtz partition function, and that is what we have done here. And then we do curve fitting and get values of Ci and Hi, which will be many, many constants. So I'll just show you a few of these formulations. Okay, here is a equation of state which fits all the data. It is not that there is only one equation which we can use for fitting all this data. We can see here, this is the first equation, P equal to RT upon V, and then a whole bunch of things put in there, which are only functions of temperature and density, explicitly. Another formulation, P equal to rho RT plus a whole bunch of other things, some sort of a variable coefficients coming in there. Then P equal to rho RT plus some other form of these combinations. Another formulation is got a whole bunch of other things, 28, 32 constants coming in over there. So that's okay. And the reason we put these is that for some materials, some equation fits best. For some other materials, some other equation fits best. So like this, we have many other equations coming in here. And the equation that is of use to us for water is this equation, P equal to rho RT multiplied by this thing. Q is a partition function which is given by this, which has got so many constants in it, or by this. This is the one used for water. So you get this big long equation which has got lots of constants which are given separately, and from there we can then put it into this equation, differentiate it as much as we want, and compute any properties that we want. So we can make our own program and say that, look, I can do this. But the trouble is, the two independent variables in all these formulations are pressure and density or specific volume. So if we know a state where pressure and enthalpy are known, then direct use of this equation is not possible. We have to develop some other techniques of interpolation and some approximation to get to the correct answer. Most of the web-based programs or others that you see may not have that flexibility, that if I specify specific enthalpy and specific entropy, what is the pressure and temperature? That question most of these programs will not be able to answer. Okay, so those are the type of equations we have. These are equations for CV0, constant volume specific heat that we were talking of. Depending on the materials, we have various types of things which have varying degrees of dependence on temperature. That's all. There is constants and temperature to various power, T square, T cube, T to the power 4, like that. The saturation pressure curves that we drew yesterday, they can be expressed by any of these type of equation. ln P is equal to some function plus function 1 by T, ln T, and things like that. Or P by Pc is a function of temperature. And so this is a 1:1 equation. You specify the temperature, you know the saturation pressure. That's what it is. There are many other formulations that are possible. Again, some are good for some substances, some are not good for others. This is a formulation for saturated liquid density. The density of the saturated liquid state, rho F, or specific volume Df, this is given as a function of this, which is only as a function of temperature. So you know the temperature, we know rho F explicitly from there. We can make similar things for rho G also. And for every material, say refrigerant 14, I'm showing you the example. The critical constants are known, Tc, Pc, rho C. The reference temperature is given T0 as 125 Kelvin, molecular weight 88.01, and the constants that are used in the equation, it tells you which is the equation that we use from those, and what are the constants to be used for that. What for saturation to pressure, which is the equation and what are the constants. And like that, we can put all these together and produce all those property tables and charts that we like to use. For water, that's the type of formulations you see. The same equation I showed you. There's so many constants that we need, even for the P rho T equation, which is Q and P6. Saturation equation has about 10 constants. Rho F has 8, CV has about 7 constants there. So that's the general way in which people have developed all these properties, and we have the benefit of using all of that in the problems that we are solving. The last thing is how we get the compressibility for ideal gases. PV equal to RT got modified, and you have come across some of these in your other courses. There are different types of equations of state. Starting here from the top left, first one is Van der Waals equation of state. You might be familiar with that. And this is P equal to RT over V minus B minus A over V square. The form that it took was that under some conditions the material is denser, in some cases it is less dense depending on the pressure and temperature. So these two terms take care of those physical phenomena of gravitational attraction and nuclear repulsion between them. Doesn't fit very well to the first equation. Then came the virial equation where Z equal to PV equal to RT was defined as a function of V temperature and specific volume square, specific volume. So it works a little better and gives you the value of Z. Then the BT Bridgman equation of state, RT upon V bar plus various constants with V bar, V square, V cube, V4. This is specific volume. Then the Benedict-Webb-Rubin equation, it gets a little more complicated, but same thing, that RT upon V plus some constant into RT plus a whole bunch of constants and combinations of temperature and specific volume. That's the common feature in all of these. V Kessler, a little more simpler, 1 plus Bt upon specific volume square, cube, fifth power, square power with T cube, and like that. The cubic equation of state, Redlich-Kwong equation of state, and so forth, depending on what one is interested in. And so you are only interested in looking at the vapor phase of a refrigerant in a compressor or in an air conditioning system, then you can say, look, this equation is good enough for me. I am not too worried about what the equation of state for the liquid thing. From there, I'll get some simple state, and from there, I'll pick up all my values. On the liquid state, I'll just say H is equal to Cp dt and get my data from there. So one can do a mix and match of some properties from here, some properties from there, and solve the problem. In our case, we won't go into those details. We'll just stick either with the ideal gas solution or we'll look at the property tables and calculate things.